So the first talk this afternoon will be with Jaco, and Jaco will be telling us about integral subsectors of AdS CFT and LLM geometries.
Thanks a lot, Robert. And let me also start by just thanking the organizers. Here that I should thank Vishnu especially for organizing this wonderful workshop. I think the talks have been excellent, and being so close to nature and being experiencing all of that has really been excellent. Really enjoyed it immensely. So the topic I want to talk to you about today is basically a project that I got started in when I started my postdoc at WITS almost 3 years ago now. And I'm going to get into exactly what it is, but as we mentioned, it's on these integrable subsectors of AdS CFT. These come about when I consider specific LLM geometries or a certain class of operators in non-planar AdS CFT. I'll get into exactly what they are in a couple of slides. Just a little bit of a background. I'm just going to tell you exactly what I'm going to be talking about, and motivate why these are interesting, discuss the gauge view description, and then consider some of the strings. These will essentially be or comprise tips of a very explicit proposal that I will make shortly. The talks that will be mostly relevant for this talk are the following ones that were maybe published in the last couple of years, especially these three over here that were published this year. You will see that it's done in conjunction with Robert and Q and a lot of them. So if any questions, feel free to ask myself or any of them, of course. And then there are also a bunch of other collaborators that are also getting involved. And there are works on related topics as well. So before I get into this, let me just make the following remark that the statements I'm going to be making, I think have been around for quite a bit, that there are non-planar sectors of AdS CFT that undergo some simplification that would possibly make them solvable, possibly even integrable. But these works I cite in the previous slide over here, what has happened in the last couple of years is at least that the statement has sharpened significantly. There's a very clear prediction of what you should find as the solutions, and there are very explicit checks that one can compute with this machinery. So just the context that we're in is AdS CFT, and I think they're all very familiar with. But there are just two remarks that are in order. The first is that the part of AdS CFT where, of course, we know an incredible amount of is planar and AdS CFT, and that's precisely because we have the power and capability at our disposal. These allow us to compute anomalous dimensions of operators, for example, validate all orders of the coupling, many other quantities at all orders of the coupling, but much less is known about the non-planar sector. So in the non-planar sector, for example, in planar AdS CFT, basis that is typically very much used is that of the single trace operators. When you go to the non-planar sector, and what I mean by this is I consider operators that don't have a bare dimension of order square root n, but of order n or larger, order n squared, for example. Then these single trace operators no longer form on a diagonal basis. The combinatoric factors, when I do the weak contractions, they just overpower everything. And you find that I can no longer use this as an orthogonal basis. However, there are tools, the shear polynomials that I will introduce shortly, that do allow you to study this in some respect. They also have some of the technical difficulties, but at least this bit I'm going to be focusing on, there's a huge simplification that takes place, and the conjecture is that this should have still the computations explicitly. So the context I'm going to be looking at, and I think it's just for illustrations, so based on the string side of the correspondence, I'm going to be looking at LLM geometries. These are half DPS regular geometries. I give here the space-time metric, so you don't need to worry too much about the details of this. When I go to the string examples later, there's going to be, I'm going to look at a submanifold of this, and I'll then be much more explicit about what these functions are. The only takeaway from this is that there's a single function z. Z here will be a function of x1, x2, and y. And if I know z, I know every other component in this metric. So with z, I can reconstruct g, I can construct the v's appearing there, I can construct h, and this whole metric is known in terms of this. And additionally, z is sourced by the Laplace equation. So if I give you an appropriate boundary condition for z, that gives me the complete z by the Laplace equation, and that z then determines every component in this LLM metric that I've written down here. The boundary conditions that are typically used are the ones on the LLM plane, where I said y is equal to 0, and it's for the following reason. When I send y to 0, you will notice that these 2 3 spheres tend to shrink to 0, because y is going to 0. However, regularity requires that it only happens for one of the 3 spheres, and that means that e to the g must go to infinity. And that can only happen if I trace the logic of these over here, when z is equal to plus 1/2 or minus 1/2. So in other words, the boundary condition can be, on the LLM plane, is just given by a coloring where I've specified z is equal to plus 1/2 as white, and z is equal to minus 1/2 as black. And I'm going to be even more specific than that. And just a little change of format from the rest of the talks. I'm just going to write a small thing here on the board just for illustration purposes. A typical boundary condition that we might be considering here is the following. I've got these concentric rings. So don't let my drawing fool you, they're supposed to be concentric. At least as follows. So I've got this alternating set of concentric rings that are black and white. As I said, z is equal to minus half corresponds to the black rings, and z is equal to plus half to the white rings. And this is a typical boundary condition that we'll be considering. So these can be mapped in a one-to-one way to Young diagrams. This is actually the point I make over here. And the way that happens is the following. So if I've got a setup like this, then I'm going to ignore the proportionality constants, but say that this inner ring has an area of n1, this has an area of n1, this an area of n2, this one of n2, and this one of n3. Then the corresponding Young diagram for this is going to have n1 empty rows, then I'm going to have n1 columns, n2, n2, and n3. So this will then be the Young diagram, and I'm going to associate with this geometry to classify these. So the areas map to rows or columns specified with Young diagram. And to be even more explicit, what you find is that Schur polynomials labeled by this Young diagram that I've put down here. So I'm going to have chi of this as a function of z. This is a collection of, or a bound state of d-branes due to this geometry. So if I put this set of d-branes, maybe it's from S5, that back react to give me the geometry specified by this boundary condition for the LLM plane. And that's the way I'm going to be thinking about that. So I've mentioned Schur polynomials, just a few short notes of what they are. So as I've already mentioned, it's a basis for operators where they're labeled by Young diagrams, and if I take a two-point function, it is always orthogonal. And this is valid at all values of the company. So even if I have all orders of n, this is true, so that's why it's a convenient basis to use in this context. It's just a basis, so if you give me anything in the trace basis that we all know and love, I can always rewrite this in terms of the Schur polynomial basis and vice versa. And as I say, for these LLM geometries, there's a very nice mapping between the Schur polynomials and the geometry that I'm considering. Just say that the vertical sides map to the black rings, and horizontal sides to white rings, and this are in the boundary condition. Alright. So, now just to get into what this proposal exactly is, as I said, the context for this is a LLM background, or these Young diagrams. And so in this 2016 paper, we defined these localized excitations of these geometries. So what are they? Well, you give me a particular background. I've just scaled things down from order n squared to something that fits on this page. But essentially, you give me some background that you have in mind, some z fields, symmetrized in a particular way.
Could you just say a little bit, how do I go from a Young tableau to an operator, please?
Oh, so that would be, I didn't actually put it explicitly, but essentially, so let's say
one simple example.
Yeah, well, one simple example. So basically, I give you, so let's just say here's R, and I've only got one complex field Z. Then what you would do is the following. I would make a sum over, so Z has n boxes, right? Then I would sum over all permutations of Xn, and then I'll have these Z's contracted in a particular way, specified by this permutation that I have over here. So I sigma 1, Z I2, I sigma 2, in way, and then Zi in sigma n. So this tells me a particular way that it's contracted. So this is a combination of single and multi-trace operators. And then the very important bit is that there's a restricted character of the symmetrical so XR of sigma.
So sigma is a bunch of cycles,
Mm-hmm.
and those are the lengths of these n1, n2, n3.
Yes.
You basically take trace to the power of the number of cycles.
Yes.
Cycles, right? Okay, I understand. And then with characters.
So like for n equal to 2, it will be a trace z square minus 2 times trace z whole square, that kind of thing. Yeah.
Yes, exactly. Now, as I said, I've just done this for a single field, but there are ways to extend this to multiple fields. We have restricted polynomials, but the idea is exactly the same. That there will be a bunch of Young diagrams labeling the different fields that I have, and I will sum over the ways that these are contracted and weight them in a particular way with these restricted characters. Now, computing these restricted characters is, I think, the main technical difficulty in working with this basis. The good thing for us, which I'm going to argue now, is that we don't actually need to compute these explicitly, because the conjecture is that the answer we're going to get at the end is related in a very simple way to the planar answer. So that I don't need to compute this explicitly. I can just say that these are done by the planar computation and just do a very simple mapping to.
I'm sorry for the ignorance, but you're using here the fact that Young tableau label representations of the symmetric.
Yes, exactly.
Thank you.
Exactly. All right, yes, so thank you for that. I think that's a crucial bit of detail that was necessary. So, as I said, I've got a particular background, so I have in mind some Z fields organized in this way, and I've got some excitation I've got in mind. In this case, it's an excitation made of 3 Z fields, 1 Y field, and there are 3 Young tableau organizing these. The first one organizes all the fields, so my 2 Z's and my Y together. The second one organizes just the Z's on their own, and the third one just the Y on its own. If I want to talk about this excitation localized at a particular corner of this Young diagram, so say I want to localize this one at that top right hand corner over there, how do I go about doing that? How do I write down an operator that represents this background plus the excitation? In this sheer polynomial language, it's done in a very natural way. You literally take these Young tableau.
Sorry, we'll ask you one more question.
Yeah, sure.
Suppose I were to compute the character of, let's say, SUN, of an SUN thing, in the representation R. And I write that character in terms of as a polynomial of traces in the fundamental representation. Does this give the expression of, is this the answer to that question? That it's the formula for the character in representation R in terms of the character in the fundamental representation?
This is the character representation of
R is written in terms of the
Exactly.
fundamental character.
Exactly.
Thank you.
So what we do to give me that operator that represents both the background and the excitation is this one over here, where I've taken these Young diagrams and I've just glued them onto the top right and each one I want this excitation to sit. I noticed that only 2 of the diagrams gets enlarged. So my background is full of Z's. I've got an excitation that's partly built out of Z's. So the 2 diagrams that contain Z's, the one with all the fields and the one with just the Z fields, need to be enlarged to include this, but the rest remains unchanged. And I just want to emphasize again with my much larger operator. So I have in mind where these size of this background scales like all the n. So you will be due to some our own geometry. And now this is quite important. Let me just also make the point that what I also have in mind is that when I attach this excitation to a particular corner, the other edges of this diagram are well separated from it, by at least all the end boxes in the Young diagram. And the reason this is essential is that in the paper we did the following and said, well, let's just add some excitation both from Z's and Y's, attach it to one of these edges, and take the one rotation operator that you know, and let it loose on this operator representing this background and excitation. So you do that, and you get 2 kinds of terms. So as I said, the dilatation operator here, it doesn't discriminate. If it sees a Z, it will act on that. So in this previous picture over here, we've got 2 kinds of possibilities. I can either mix the fields at this edge, so there are Z's and Y's, they can either be mixed up in some way. I can also take one of the fields from this excitation and glue it after acting with the dilatation operator on this side, or I can take a Z field coming from the background and that moves into the excitation in some way. Those are the possibilities. You group those terms together and you see what you get. And I've labeled them in.
Go back one track.
Sure.
Those, the row of 3, they were made, what do you mean Z, comma, Y? It could be either Z or Y, those?
Oh, so it's, so as I said, this Young diagram organizes all the fields that you have, so your Z's and Y's, you've got 3 of them. The second one organizes just the Z's on their own. So
But how many Z's and how many Y?
2 Z's and 1 Y. So the last one.
There's always one Y.
So you can have multiple more Y's. In this example, I've given you just that one, primarily for space constraints.
Okay, thank you.
Slide, but
And what did it mean that there was a box down there?
oh, this will again be, so what you're going to have in mind here is a restricted shear polynomial. Again, this is a diagram organizing all the Z's and Y's that you have in the operator. This is one organizing just the Z's, and then I'll still have just the 1 Y and this one.
So no symmetrization, no relationship between the two? What does it mean that there's a comma in there?
I'll put this.
So the first Young diagram is a representation of S of all of the fields. And that one you can restrict to a subgroup that swaps only the Z's and only the Y's. The second 2 Young diagrams would be a representation for that subgroup.
I see. Thank you.
Yes.
Thank you.
So just getting back here, so basically you have these 2 kinds of terms that you have. One that keeps just cycles the fields in the excitation and doesn't mix the background and the trace together. And what we showed is that these, the ones of the second kind, precisely because this excitation is far separated from this corner and far separated from that corner, what you will get is that terms of the second kind scale like 1 over n. So if I send into infinity, I only get terms of the first kind. So the dilatation operator, if you will, only acts locally on this excitation, and I've localized a particular edge.
It doesn't move it too far in the Young diagram.
Yes, exactly. In this case, in fact, it can't move anywhere because the only other possible location for it to move to is separated by all the boxes. So it is. So the dilatation operator doesn't mix it at all with any of the other localized operators. And what you find furthermore is that the only difference that you get in the action of the dilatation operator is an effective rescaling of the truth coupling. So, say for example, I take a single trace operator like this. So what I can do with the single trace operator, rewrite it in terms of shear polynomial basis. I can know how to localize each of these individually. So this being localized in a particular corner is now some linear combination of shears. I act with the dilatation operator on this object that I have over here. Then the action of that dilatation operator, as it is for just if the dilatation operator is acting on this, it's like a spin chain Hamiltonian. But the only difference now is that the truth coupling has to be rescaled. But that is the only difference. At least this is the claim. And this is
Difference with what?
So if you had no background there, so let's say that this is an operator for planar energy with 4 superangles. I let the dilatation operator loose on this. The dilatation operator is like a spin chain Hamiltonian. It has a diagonal piece and a permutation piece. We get exactly those same pieces appearing, where I've got the excitation attached to the background. The only difference is going to be that there's going to be a rescaling of the truth coupling. But otherwise, the form of the Hamiltonian is exactly the same. You'll still have a diagonal piece, a permutation piece, and as I said, this is checked explicitly at the 1.
So your background is made up only of Zs, and you've got this excitation with the background, and you're saying that basically rescales.
Yes, exactly.
Sorry, what about the boundary terms? So, I don't understand. So if you put a long string on top of some D-brane, there are terms that have to do with interaction of impurities with the D-brane.
Yes.
So those are not just
so those are the ones that in this context scale up 1 over n. So
yeah, but there might be n of them. So that's how you get that's how you get this bound state.
I think
it is true that there are 1 over suppressed, but in some cases there's n of them.
I see. So I think the thing that happens here is because I'm considering these ones with well separated corners, I only have all the 1 of these possible exchanges that can happen, and each one of those all the 1s are suppressed by 1 over n. So that
does this apply to the determinant glued to a string? Because that's the case exactly that I'm talking about, right? Where there are interactions between the impurities and the edge. And those are exactly these kind of terms that are suppressed, and there's n of them.
So in that situation, the description is slightly different.
Ah,
And
so
the
it
reason
doesn't
for
apply to
that, it doesn't apply to this. In that situation, your string is described by a word,
Yeah,
and two of the indices are attached to that box in
That's
the Venn
right.
diagram.
that's right.
In this situation, every single field inside the excitation is a box inside that Young diagram. So in the case of the giant that you consider, most of those indices are not symmetrized with the rest of the fields inside the determinant. Here, all of the fields inside your excitation are symmetrized with the Young diagram, so they're kind of glued in place.
Sorry, but then I don't understand. So what kind of states am I describing with this? It's not all of them, yeah?
No. There are others. This is not all of them.
Oh. So which ones are they?
So
How
those,
do I name?
that thing that you're thinking about,
Yeah.
the maximal giant would sit at the origin of the LLM plane.
Yeah, for
The
example.
open string word, those magnons would stretch to the circle at radius
That's right.
1 and then all stay at circle of radius 1.
That's right.
This could be, say, a giant orbiting at some smaller radius, and all of the magnons are attached to that smaller radius. So those are the states that you're considering, where everything is localized
Oh.
at the radius of the giant.
So these excitations could be either open strings or closed strings, or
Well, these are all sort of excitations of the rows of the Young diagram, which is a D-ring. So from that point of view, they definitely all describe it as open strings. So you'll be getting the gauge theory on the D-ring. There should still be a gravitational dual. I guess that would be in terms of those strings.
But doesn't it make a difference that in the usual determinant case it's order n boxes, here it's order n squared, right? Or you're not thinking that that doesn't play a role in the suppression?
The difference really is that every single box in the Young diagram corresponds to a field inside your excitation. It's not that you put a whole word into that box. So even though you have this enormous background, if you were to stick an open string word as Diego was suggesting, you would find exactly what he was saying.
And I have one question. What was it effective again?
Oh, so this is actually what I wanted to, and that is the next point. So, because what is ineffective now is, so in your Young diagram, you've got weight of a particular box. So the top left-hand corner will be n, and then if I move one column to the right, the effective weight is added with 1, or the weight is added with 1 of the box. So for example, this one will be n plus 4. And if I go down, I need to subtract 1. So the weight of this one over here will be n minus 3. And what I have in mind in effective over here is that it's exactly that weight of the box where I'm attaching the excitation to. Yes. So, but the point is, as I said, when we go to the string theory side, but this is just a rescaling we're going to be seeing, a rescaling of the top coupling.
But you want n effective to be large, right? Because
you want that to be
n to infinity, so you want n effective to also be.
Exactly. You want that ratio to be an order 1 number. So that's what you want to see. Yes, exactly. So in effective will be large. It will scale like n, so that R0 will be an order 1 that we scaling with the top coupling.
So you're going to consider very large operator. That's what forces you.
Yes, precisely. All right. So this is what we meant by localized excitations. And as I said, this is the prediction coming from the one-loop dilatation operator on these localized excitations. And the paper that Robert put out a couple of months ago, I think this is stated very clearly what you have in mind. I'm not explaining it correctly, but the idea here is that if I consider localized excitation, so I consider these excitations where I add all the boxes to a single corner of the Young diagram, this gives rise to an emergent gauge theory. You're not mixing with any of the other corners, so under the actual dilatation operator they are still stuck at the corner, and you get some emergent gauge theory coming out. If I take the planar limit of that emergent gauge theory, it should be isomorphic to energy equal to 4 superangles. And this is due to the following 3 statements that is proven in the paper. The first is that there's an isomorphism between operators. So for every operator in planar energy equal to 4 superangles, I can find a localized operator matching it. The scaling dimensions match, and the 3-point functions of these directions. So I have a list of possible operators, I have a list of the scaling dimensions, and I have a list of the e-coefficients. And if these match, then it must be an isomorphism between these two. And this is essentially what we want to test. And as I said, this is a very sharp statement. All you should see is this effective rescaling of the 12th coupling theorem. So this is a very concrete conjecture for these localized operators. that we want to test. And I'm going to continue testing it in one test in the gauge theory and two kinds of string excitation. And I'll in background and show that this rescaling of the tooth coupling is really the only difference that you see. So
3-point functions vanish just because they're 1 by n.
One of the
Collected.
Exactly. So the gauge theory, I've already given one of the tests. That was the one with the dilatation operator. But I should add that with a footnote. If you were skeptical of the one with dilatation operator computation, as I said, this was done quite explicitly. All the terms are collected. The ones are shown to scale up one of the ends, so that they really disappear. And this operator is really localized, and you only have this reasonable crossing. However, you would say that what you have with a background of Z fields in your excitation, and the number of impurities, is a residual HT2 squared symmetry. This has been applied in the case of these elastic scattering conditions, reflecting magnons, also in this case where you have, so this is where you have a string attached to a maximal giant, and this is where you have it attached to a non-maximal giant. The symmetry argument works exactly, and you can write down, for example, the exact dispersion relation of that one impurity, a single one impurity exactly, valid at all orders of the coupling. If I expand this orders of Lambda, then I'll just get terms in ascending order of the dilatation operator, the eigenvalues of these. If I restrict them to lie on a single corner, this is the case that we're going to be interested in, then all you see is the dispersion relation of the giant magnon, but with a rescale coupling. This is all you see from just the symmetry argument. So the point is that you would say that at one dilatation operator computation, and of course you also determine the kinematic part of the S matrix exactly. You would say that, well, all you've computed with one dilatation operator computation is something that's already dictated by the symmetries to be of a particular form. So the fact that you find that is perhaps not that surprising. And if we really want to test if this is correct, we need to not just compute the kinematic part of the S matrix, but the overall dynamical phase. That's not determined by the symmetry argument. And for that, we're going to need to go to 2 loops in the dilatation operator. Then you get a contribution coming from the overall dynamical phase. I should just make a comment here that you will see that what I have here is a dispersion relation where I've actually got a pretty general one impurity, one that stretches between 2 different corners. And the way this is constructed is, well, I've already showed in the previous slide how I localize it at a single corner. So this is exactly what you do. I take 2 excitations, localize them in 2 different corners. And here I've got placeholder field V and the placeholder field W. I have in mind replacing these by Y's. But what's going to happen now is that when I act with this operator over here, I'm going to replace the W with a Y stretching between corner 1 to corner 2, and I'm going to replace the V with a Y stretching between corner 2 to corner 1. And what I mean by that stretching is that to its right-hand side it will have Z's at a particular corner, and on its left-hand side it will have Z's located at the other corner. But this is an operator that you can construct. This is the dispersion relation that you should get from that. And these are the ones that we'd also like to consider in our symmetry argument to make sure that everything is consistent and working.
Sorry, you said, well, maybe you're exactly going to say something about this, and that you call this dynamical phase. But it's not, that phase is not fixed by the supersymmetry, that's true.
Yes.
But it is fixed by integrability, right? So
absolutely, yes.
So in some sense, it is determined by the symmetry.
Yes.
It's just it's not determined by supersymmetry.
Exactly. Well, what we're after in the end, so if the statement is that the emergent gauge theory at this particular corner as isomorphic to NS equal 4 superangles, it should also be integrable. But what we don't want to do is assume integrability, thus compute that phase and get an answer. We want to just show that the answer we get is consistent with assuming integrability, computing that phase. And that is what you get. Exactly.
And the statement that all that changes is a renormalization of lambda, was that a one-loop statement or an all-loop statement?
So thus far I've only shown you the argument to one loop. What I'm going to do now is to give some evidence that we have that this is true at 2 loops, and give you some evidence that this is true in the strong coupling. But the conjecture is that this should be true at all orders of the coupling. So if you go up to any order of the dilatation operator, this should be the only effect you see.
Sorry, for that line where R1 equals R2,
yes,
that's very easy to show that's true to all orders.
Yes.
In that case, I think it's obvious that it's true to all orders.
Yeah, but maybe I remember wrong. I thought the dynamical phase comes at 3 loops, or am I?
There's in phase? Yeah, Should be 3 loops? Yeah, or 4.
At 4 loops.
Yeah, so why is it 2 loops here? Or are you saying that your results are consistent with that?
Oh yes,
But it could still be 0 2 loops? Or?
I need to recheck the computation for this.
I guess Jaco's not calculating the phase at 2
Yeah,
loops,
yeah.
he's just checking the anomalous dimension at 2 loops.
Uh-huh.
To calculate the phase at strong coupling.
Okay.
Yes.
No, for strong coupling, sure. But okay, you're not actually finding a dynamical phase at 2 loops.
No.
That would
That's
be quite different from the
No,
standard.
so the next slide will just be showing that, so you have the symmetry argument that determines the kinematic piece. You can still diagonalize the 2-loop dilatation operator, find those kinematic pieces, make sure that they match completely with this rescaled coupling. Or that this is consistent with this kind. Exactly.
Also to see that with coupling you need to put in all the whole, you cannot stay within one subsector, because if you have just one subsector and integrability, there are other phases that will be consistent at 4 loops. So what fixes uniquely is you have to look at all of the sectors at the same time.
Yeah, but there is also a coupling dependence in this resin phase, so it's still gonna be like rescaled by R0 when
Yes, so the claim would be that if you compute that, that should also
strong
show
coupling.
us-
Maybe you can check that that's what it's gonna.
Absolutely. Right, so this first statement I actually already made, that this is already determined just from symmetry alone. And now the way to go forward, and I'm actually going to be really quick, unfortunately, because I actually want to focus more on the strong coupling side of this picture. But basically all you need to do is write down the 2-loop dilatation operator, you know what all those terms are. Then you're going to make some sort of beta ansatz. So I introduce here these wave functions related to the sequence of, I've got a C of z's and these 2 impurities. The position that the y is in, I'm going to call L1, and the position that the x is in, I'm going to call L2, and I'm going to relate the wave function to this in a particular way. I can now let the dilatation operator loose on this object, get a series of expressions for these wave functions that I have over here. I diagonalize the dilatation operator, get the energies, make sure that they match, which they do, and make sure that the kinematic modification match, which they also do. But this is just for a simple case where these are considering a planar operator and using it before. The case that we're interested in is one where, well, let's keep it as general as possible. I've got these impurities and they stretch between different corners in my own diagram. So I've got a y that stretches between corner 1 and corner 2, and an x that stretches between corner 2 and corner 3. I can again write down these wave functions, and then you still get the same kinds of terms in the dilatation operator. What you must do is make a rescaling of them. The rescaling is, well, I'll just give an example here. If there's a swap occurring between them and there are 2 different edges, then you need to rescale by a factor as that. But in the paper we do write this down quite explicitly. You can again diagonalize a 2-loop dilatation operator. Just one thing to point out is that in this case I've written down 2 bosonic impurities, y and x. At 2 loops, you need to take into account the fermions as well. It's quite important. But you take all these terms into account, write down an ansatz for them, plug it into Mathematica, wait about 15 minutes, and it spits out an answer for you. And you can check that the dispersion relation you get matches exactly with the prediction, and the S matrix matches exactly with the prediction. So things are definitely working in this 2-loop computation on the gauge theory side. I can make a footnote that in principle, all the machinery is in place to do a 3-loop check as well. I would suspect that this would be, it's a lot of terms to keep track of, difficult to manage, but certainly doable.
Sorry, one comment. I do not remember, maybe some other expert remembers, but the reflection part of the scattering, I'm not sure if the phase only appears at 4 loops. Maybe it appears sooner. I don't know. So maybe you can, maybe there is something you could check. I don't remember, but
that
maybe it appears sooner for the reflection.
Absolutely, that could definitely be.
But I don't know.
Absolutely.
It depends on the case.
It depends
one
on
of
the
the cases it can be written in terms of the bulk resin phase, so I think it's gonna appear at 4 loops.
But the reflection is like, it's like more or less like one. It's like one, each loop is like 2 loops, right? Because so I don't know. So okay, I don't know. I don't remember. You have some chance to see something sooner.
That would definitely be interesting.
Reflection.
Absolutely.
Sorry, I think I'm still missing the picture of what is your generalized spin change. Are you thinking of a spin change for each row or something like that? We don't have a trace operator now, right?
So the point is that what you can do with that, so I still have in mind, as I said, actually the dilatation operator is only this rescaling. So in other words, this spin chain picture that you have for these trace operators, if what I do is I take the trace operator, rewrite it in terms of shear polynomials, attach it to a corner, and now ask it what's the actual dilatation operator in this. It's completely consistent to still think of that as a spin chain, provided I rescale the coupling accordingly. But that picture should still survive. That's actually the essential point here. That if you take single trace operators for which I have this nice spin chain picture, and you attach them in the prescription I gave to a particular corner, then it's completely consistent to still think of it as a spin chain of a rescale coupling.
But in general, you can have many corners and many of these operators.
Yes,
so
exactly.
I think separately one S matrix for each one.
Yeah, but the thing is that if I scale over this pretty quickly, but if you do this, then what you get is it's still consistent to think of this as a spin chain. But what happens now in the spin chain is that the dynamics are a bit more interesting in that the Y impurities that stretch between corners stretch between different regimes of this rescale coupling. So, and this is something that you need to take into account, but you can do this completely, but it's completely consistent to think of it in that way.
Roughly, am I thinking of this as a string in the background created by the other stuff?
Yes, absolutely. In fact, when we go to this to the string side of it, this is going to be quite explicit that this is what you should see.
And things at different corners will be in different places in that geometry.
Yes, exactly. So in fact, the way it's going to enter is different boundary conditions for the string should localize it in a particular place, and that's where you should see this rescale coupling.
So what's the rate? But any interaction would split your individual single trace operator, like splitting and joining things, is subleading, right? So
yes.
Yeah. So I can just think of it as having several independent single trace spin chains and S matrix action each one.
Absolutely, yes.
Now, so imagine that you are in a annulus case, right? So you can have like excitations that the giant magnon goes from the outer rim to the outer rim, and then you have two of them and they scatter. Why is it not possible that for some momenta they are gonna, after the scattering, you can also get like two giant magnons that connect the outer with the inner? Because so there might be some lengths such that the quantum numbers of the representations, that what is the thing you really have to preserve in the scattering.
Yes, so you know, if you were to just think of it as a, so you can think of this as the quantum numbers giving you some classical scattering process. I need to conserve total momentum, I need to conserve energy, I need to conserve the charges of my excitations. And this gives you set of constraints for what the final momentum could be. So, and of course, if they're on the same edge, I just get elastic scattering from that. The reason that I would say you wouldn't get the process where they move from an edge and move to another one, simply because in order to do that process, I need to remove a very large number of boxes from a particular corner and stick that at another one. But that might be a bit of a naive picture that I have. But, so that's why that process should be highly suppressed.
From symmetry point of view, I mean, preserving. I mean, you have to preserve is the starting point of the where one magnon is beginning and the second where it's ending, and then you have to preserve the energy, which is the sum of the lengths. But it could be like the sum of the lengths is preserved when you connect to from the same initial and final points to some. So from symmetry reason, you might think that, but maybe you're right. So then this is suppressed somehow. But for symmetry, thinking just in symmetry, it might seem possible.
Yes. So we did do the computation for if you have inelastic magnon scattering, and did this comparison. And I know that in that case you get the unique solution for what the energies could be. I'm not sure if that applies to this guy. I need to recheck the computation.
So you say that when the impurities cross, so say you have sets on the edges, some sets in the middle, they cross, and then when they leave, they have something stuck in the middle.
Or some this.
Let me make a comment. So in fact, kinematics alone won't prevent that process from happening.
Right.
So you could, for example, stick edges on the plane so that if you're on that edge or you're on the inner edge, you satisfy the kinematic constraint.
That's my concern.
Okay, so here's the point. When you're sticking things onto a certain fauna, you're sticking things onto a certain D-brane.
Right.
When you think about these open strings, there's a channel pattern factor associated with the end point of that open string. If you switch off the string coupling, those channel pattern factors don't change. Open strings cannot split and join. So the process, you can calculate here, the process where you flip to a different edge is 1 over n separates.
Okay.
Yeah.
It's because you need to make higher traces stuff in the middle, right? That's what it means.
Exactly.
Switching means that instead of having just sets in the middle, you have some stuff that's like higher trace, right? Imagine if you switched all the way into, say, to a giant, you need to make a determinant inside, right? So it's always suppressed by more traces, I think, that you need to put inside.
Okay. Thanks for that. So I see I have about 20 minutes. I'm just gonna. So I will try to cover as much of this as I can, but I will definitely show all the results at least that we have on the screen side. So the first computation I have is well, let me just say I'm going to be considering point-like strings first. What I'm going to do is I'm going to take the LLM metric and I'm just going to consider a submanifold of T R phi on the LLM plane, y is equal to 0. This is quite consistent to do the equation of motion you get by doing this before or after it's completely fine. So I can just consider strings on this submanifold. And now once I've restricted to the LLM plane, there's a very explicit formula I write for V phi. So V phi is essentially the sum of poles of different radii that you have. These radii are exactly the radii of the rings on the LLM plane that I have over here. So each ring edge, this represents a geodesic, and this is represented by a pole that you have in V phi. And there's a factor in front that's determined by whether it's a black or white ring and whether you're considering everything on the inside of the radius, outside of the radius. But that's not going to be too important for computations. The important takeaway is there's a pole represented in V phi whenever I encounter a geodesic on the LLM plane. And then H is given by this simple relation here with respect to V phi. And again, the poles are going to play a role over here. Now what happens if I point-like strings, you can quickly show that this solves the equation of motion for any LLM geometry, any choice of V phi. I get exactly what I should. It's a half BPS operator, so easy to J. No problems there. And these rotate along geodesics at the speed of light. The key difference is that in the AdS 5 plus S5 case, where I have only a single black ring labeling the geometry, in this case I've got several rings. So I've got several possible choices of geodesic that works. Any one of them is a legal choice for your point-like strings. And this will present a technical difficulty when we go forward. So you need to take this into account, that there are many possible boundary conditions that I can impose on these strings. And secondly, it presents another interesting thing that we want to eventually isolate an integrable subsector of the theory. But the point is that string theory on this background over here is not integrable. You've got boundary conditions like impose on the string that will give rise to inelastic scattering processes that don't satisfy Baxter. So string theory on this background is not integrable. It's only when I take all the stringing excitations living on this background, I, from those, only take those that have the appropriate boundary conditions that I should then give rise to some integrable subsector, and then you will only see this rescaling of the color. When I go to the issue 2 strings, I will show this quite explicitly that you can write on these stringing solutions that stretch between different edges and exhibit inelastic scattering. So this is for the point-like string, this is just a solution that you get. So no changes from the AdS 5 case, except for this.
Sure. I mean, this is just a state in n equals 4 GM nodes, right?
Yes.
And you are in the planar limit. So where is the non-integrability limit?
Oh, so for point-like strings, it's often there. So you're still just stuck in a single geodesic. But when I go to the strings where I've now added some impurities, now I will start to get some more freedom.
No, but still, string theory I would expect to be integrable. If you don't have any
planar limit. This is not the planar limit.
It's not the usual planar limit, but
it's not the planar limit.
Oh, okay. It's before we take the planar limit.
No, you've got order n squared boxes in your operator. If you were to just sum the planar diagrams, you would get a very poor approximation to the correlation functions. When you sum everything, this agrees with the planar limit of some other n is equal to 4 GMLs. But to get the answers that Jaco is getting in the gauge theory, you need to sum all ribbon graphs and then take n to infinity. Not just planar graphs.
I think it's a matter of convention. What we call the planar limit, I mean, this is still the leading large n limit.
Exactly.
So it's, from the string point of view, it's free strings. So, but what he's saying that we have, you cannot think of traces because you have this order n square.
No, sure, but I would expect, I mean, if T string is going to 0, that string motion will be integrable.
One example where that's not true is black hole. Black hole is a classical solution in string theory, and strings in the black hole are not integrable.
No, but that's thermal, right? I mean, you've put the thermal.
It doesn't matter. From the point of view of gravity, it's just a solution of Einstein's equation. This is also a solution of extension. Sure. So not every string motion is not integrable in every classical solution.
Yeah.
In AdS5 it is integral, but in this LLM geometry it's
Yeah, I mean, even the AdS solid form or something like that.
You know,
It's not
no,
even-
but all these things are changing the boundary condition. I mean, because
These are changing.
so
The reason I'm making this point, I should just add that, is that what you would do in AdS5 is follow. What you could do is something like a pole wire reduction, and that really elucidates the integrable structure. In this picture, that's not going to work. The strategy line just simply won't do that for you. So, as I said, I've discussed the point-like strings. Now we're just going to do something a bit more general, and just schematically the operator I have in mind is a single line purity stretching between two edges. I've got some phase representing the position or what it is. This is Giant Magnon. And you again just write down the equations of motion for this, take number go to. You can show that for any LLM geometry, this is a solution. So just C over cosine of phi plus t. I have not specified a whole sheet parameterization of this yet, but you can write down the definition for the conserved charges, compute these, and then this is the final answer that you come with. Completely consistent with the answer we have. So the C and phi 0 that I've left here, these you specify by means of the boundary conditions. Again, you've got this freedom to choose the string to end on any one of the edges. That endpoint D can't be the same, and this is then the dispersion relation that you get. And this completely matches provided that we identify the momentum with the angle that the string sustains. As long as you do that, everything is completely consistent. So you definitely identify the strings due to these giant magnons stretching between corners. But again, the symmetry argument will tell you that maybe you should do a little bit more. And let's try to compute the finite size corrections. The finite size corrections via the issue corrections feed from the dynamical phase of the S matrix. So if you do that, then if the statement is true that all you should see is a rescaling coupling, then you should see just a rescaling in the issue corrections, in the finite size corrections. So just to be a bit schematic, what I have in mind is some Y purity stretching between Z's, but I don't have an infinite number of Z's. I have some finite number labeled by J. You can consider the case where they stretch between different corners, and I'll give this result. But first, we'll just consider the case where I've isolated at a particular corner of this. So the way to do this on the string side is to say the following. Previously, I had R as a function of phi plus t. This represented two things for me, that you've got a string solution that retains its shape, and the endpoints live on a geodesic when I rotate at the speed of light. What you want now is something that retains its shape, but its endpoints don't rotate at the speed of light. It's lifted slightly off the geodesic. So I want a number kappa here that's slightly less than 1, perturbatively less than 1, and let's try to write down those solutions. I can choose a Walsh parameterization such that, so phi is equal to sigma minus tau, R is now just a function of sigma. That simplifies things a little for me. And you can find the solution from those equations of motion. As you can see, things are already a little bit more interesting. Unlike for the point-like strings and giant magnons, those were just solutions in any LLM background. In this case, the specifics of the LLM background enters through the functions we define.
Yeah, how maybe it's a related question. So let's take just a point-like particles before we stretch them. So you want to pull them from the equator.
Yes.
What stabilizes them? Why don't they? Yeah, why do they stay in? Why don't they just go out? What's the forces keeping them in?
So Diego, as well as I'm not perfectly sure. So essentially,
So you say the solutions are stable. You can grab a particle, have it spin at something that's less than the speed of light, and they will stay there.
So from that, I need to think a little bit more. But essentially,
In the case of the sphere, what's keeping them in is that the sphere, you run out of the sphere, right?
yes,
It's a maximum circle, and that's it. You cannot keep them. You cannot slide off. But if you want to have a circle that's smaller than the equator, what's keeping them in?
I need to think about that. But what we're doing is we're taking solutions that are known for the AdS5 plus S5 case, and just trying to write down the equivalent one for the LLM geometry. So it must be stable for some reason, but I'm afraid I don't have the explicit.
It's stuck on a D-brain.
No. That's fine. You can do that, but that's not the same as doing that, right? You can of course put it on a D-brain, which is the edge of some circle,
yeah.
And then that's fine. I don't have an issue with that, but that's not the same thing as grabbing just a trace and cutting off sets, right? If you just cut offsets from a say long string that's open, then it's like moving the point into the black region, not
These
to the
big
edge.
bunch of these can move on the edge of any black region.
On the edge, on a,
Yeah.
but
So he's stretching between edges.
I know, but that's not the operator that he wrote. That operator is not something stretching between edges,
So-
right?
so
Because
that-
there's nothing attached to the end of those sets, right?
Those Z1s are boxes in the Young diagram, which are, attached to one of the branes.
Oh, he's omitting the
Yeah,
edges. Oh, there's some
exactly.
operator at the edges.
Yes.
Yeah.
Oh, I see. It's not just.
Yeah.
So it's not that operator.
No, it's not.
I see.
Yeah.
Good. Yeah.
So, as I said, this is just a solution that you get. You can always make a change of coordinates from integrating of a signal field with surcharges to R. As I pointed out at the point like strings, you will now have several possible choices for boundary conditions. So, if I require that to keep in line with the finite size giant magnon and AdS S5, I'm going to say that somewhere in the middle there's a point where R prime is 0, and that its edges R prime should go to infinity. The point is that there are multiple possible choices for this. Well, I'm relatively close to any of the geodesics this works, and this can be taken into account in your solution. And the point is that what you would do previously is say, I give you a value for kappa, and in the AdS5 plus S5 case, you then say, well, what's the radius? In this problem, you can't do that because there are multiple solutions. But what you can do is invert that problem and ask, but I want the string edges to be close to a particular geodesic. What should the value of kappa be to give me that? And that's the one I'm answering over here. Then there's just a change of coordinates also incorporated here. Instead of integrating R, integrating over Z. The only information of V phi that I give it is that when Z goes to 0, I hit a geodesic in the problem. And all the integrals you wish to evaluate are, I integrate from f to 1, where f is really close to 0. In the paper we show how these can be expanded in a systematic way to give all the long f pieces that you need. But then you've got expressions for E, J, and P in terms of C and F. You just invert two of those relations to give E in terms of J and P, and the answer you get is the following. So here you will see that the leading order piece is that of the giant magnet attached to a single edge. And then I've got this piece where I send J0 to infinity, then I'm just going to get the leading order piece. And I just want to point out this, whenever a lambda is, there's this rescaling with respect to R0, even here in the exponent. And this J0 minus V. So what you have when I compute the J0 is I get a quantity like this. When I get J0 minus V, I get a quantity that really isolates the contribution coming from a single edge. So this is the one that I associate as the length of this operator. So that really there's the only difference you see is this rescaling of the couple. I see I have about 5 minutes left, so I'm just quickly going to run through the rest. Here's just the expressions you get if I consider the finite size corrections for magnets between different edges. This is something that you can do. We hope to use this in future to learn something interesting. I was discussing earlier that it might be interesting to consider a case where one of the R's goes to 0, so you're considering something like a reflecting magnon case. This could be something interesting, but it's in the computation that you can get to this. For the Dyonic Giant Magnon, just got solutions where I've taken not just one Y, but a large number of Y's. So that means I need to include an additional center of charge. You do that by including an additional angle on your submanifold. This is the solution that you get. This is the answer that you get for the infinite size Dyonic Giant Magnon, completely consistent with the symmetry argument. When I go to the finite size corrections, this is just the expression that you get in the end. And again, wherever I see a lambda, I see this rescaling appear, even in the finite size corrections. As I mentioned, for the Lucia corrections, this means that I take the dynamical phase, put it through some machinery, it spits out a number. That number is just rescale. So this is very strong evidence that the dynamical phase strong coupling also just shows this rescale. Lastly, in the last couple of minutes, I just want to mention the last result that we published a couple of months ago. So, as I've already mentioned a couple of times, the issue 2 to squared symmetry is highly restrictive. And it's good to do a test away from this very restrictive symmetry. And a possibility to look at is, well, I don't consider operators both out of Z's and Y's, but out of Z's and covariant derivatives of Z's. These are like the SL2 sector, and at least as far as I'm aware, there isn't a symmetry argument that will restrict things in such a dramatic way. So you can write down the solutions. This is just the solution that you get. I impose a formal gauge, and so the solutions that you get can again live at any of the ring edges. You can choose some maximal radius for it. The only exception is when alpha is equal to minus kappa, because then you have in mind again a point-like string rotating on a GMB set, but for any other choices, you can choose S, so the number of covariant derivatives to give you a finite radius. Just one very interesting thing I want to point out with these string solutions that might be helpful when studying ones in future is the following. What we discovered when we did this was that the classical string length, so here I take a number of action, I take a particular time slice of it and I integrate it to sigma to give me string length. This is some expression given in terms of v phi, and I think e to the g plus should be h squared, something like that. But this is some expression that you get. What you find is that if I take this expression and I do derivatives with respect to these numbers parameterizing the string solution, I get exactly the conserved chances. So taking a derivative with respect to kappa will give me e, double of omega will give me s, and with respect to j, or with respect to alpha will give me j. A very similar relationship here for the Giant Magnon solution. So again, you give me the classical string length, and you give me the center extension, that's the only difference, but you give me those two, and I can compute all the conserved charges in a particular way. So there's a single function you need to know in order to compute these charges. And this is something interesting to think about, I think. But so again, this is a integral that you can't do analytically. So like before, when we did the finite size corrections, we need to take some limit and try to compute in those. And the limit we chose is the short string limit. And this way you guaranteed, and I'm describing some operator at the edge localized to one of the planar limit. And the expression you get is this. So e squared is equal to j squared plus 2s. And again, whenever land out here, it's just this rescaling of the color. And that's the only difference between the dispersion relations. So these are the results that we have so far. So just to summarize, some computations from the gauge theory showed exactly this prediction. We studied SU2 strings, exactly the position of the same for SL2 strings. But there are of course many other checks that you can do. As I said, the claim should be that for all orders of the coupling and for any operator from the planar limit that you attach to a corner, this should work. So many possibilities you can investigate: scattering solutions, multi-spin string solutions, even quantum corrections to these spectra should work. The second point is, can the integrable structure be made explicit? So as I mentioned, something like a Paul-Meyer reduction on the string side is something that we would trick for you. You're going to have to think of a different approach to do it, and this I think is a very interesting problem. And then for the case where there's switch between different edges, there are possibly some interesting limits one would consider where you can also read. And then also study V-brains that you attach to a particular corner and study their dynamics. That's very interesting. But that's all I have. Thank you for your attention. I should mention it's supported by the clothing information.
We had a number of questions, but there's still time for any lingering questions.
I didn't understand all the details in your talk, but is your prediction that the spectrum of small strings, let's say not too big, not doing anything dramatic, inside any of these LLM backgrounds is the same as that in flat space up to the straight scale?
Provided that the boundary conditions are such that they are localized at a single ring.
Let's say they're. So this is then the statement that this sigma model is secretly the same as the sigma model on AdS?
Yes, exactly. That is the claim.
It sounds like an incredible thing.
Yeah, I think maybe that's too strong.
Too strong.
If you take, so this sigma model on the LLM background would have solutions where the string would stretch between different corners and all of that. There's a subsector of solutions where it's totally localized on the edge of one ring, and those sets of solutions, if you calculate their energy, spectra, whatever, scattering of Magnons on the wall sheet, that would match what you would get in the AdS5 plus S5 background.
What do you mean by total? The strings are closed strings, right?
Yeah.
What do you mean by totally localized at the edge of the ring?
So if you have a closed string like this, for example, so all of the Magnons are stretching between corners of the outside of one ring, but you could also contemplate something where it starts from there, goes to a different ring, comes into the inner ring and goes there.
Do I need to think of these Magnons? Can't I just look at small strings?
Yeah, but Robert, even in the example you consider when they all get connected to the same ring,
Yep.
you have somehow to restrict the momentum of the magnon. Otherwise, when it is too long, the classical string solution is going to get very close to the inner ring. So why is that the string does not realize that there could be even an intersection with the ring. If you imagine the angles, no? You start to increase the momentum. You cannot make it pi because before that the string would be touching the inner ring.
Yeah.
So
in terms of this picture, I guess I don't know.
Sorry, to have it detached. So if the string is really attached to the edges,
Yeah.
it has to have determinants, higher trace stuff
Yeah.
at the edges. That's what it means to attach to the edges. It means that you have all this different multi-trace stuff, and then you'd have strings linking them. And for you to have that, it means that some string gets loose from some multi-trace guy and attaches to some other multi-trace guy. And that process is suppressed a large one.
That's the only way you would see that there is a difference.
maybe because I'm thinking that, because when I consider different, I was thinking always on closed strings, and I imagine the determinant, or you have many determinants, and just a single trace on top of that. And then
that would not correspond to one of these.
Yeah, maybe.
That is not one of these.
It's not the same. Well,
Yeah.
Well, maybe I have the same confusion. Am I allowed to think of a small string sitting inside the background, an LLM background? Just a small string, something awesome. The 1,000 things I could say to string.
I don't think so. So I don't think that's the picture for the following reason. I think that these are open string excitations of the deep brain. So these are the open strings of the emergent gauge theory of the giant. There is a holographic dual to that gauge theory that would involve closed strings, but I don't think that's closed strings on the LLM background.
I mean, all of the deep brains have become the LLM background.
Yeah.
All of the excitations are closed strings on that background.
Well, you had the original ND3s,
And
that
then
was Minkowski space, and n is equal to 4 super angles of Minkowski, and the holographic dual to that was closed strings on a different background, the AdS5 cross S5 background.
yes.
Now here you have the world volume of the giants inside this LLM geometry, and open strings on that world volume. If you think about the holographic dual to that gauge theory on the giant world volume, I think it can have a different geometry in the same way that the n is equal to 4 super angles of Minkowski was dual to gravity in AdS5 cross S5. Here, what's the
I'm probably getting very confused, but let me state my confusion.
Okay.
Yeah, you've got this big operator which is making the LLM geometry, right?
Yeah,
And on top of that, you're putting that, and you said a relatively small excitation. Is this right?
that's correct.
So that sounds like turning on a string inside the geometry of the LLM geometry.
Open strings, yes.
There's no open string, it's only closed strings.
Well, you see, each row of the Young diagram corresponds to a giant graviton. So some giant graviton that has gotten big in...
So the operators look a bit, so imagine, say you have a determinant, where you open up the determinant, and then there you glue a string, right, a word.
Sounds good. So if you have one determinant, that's fine.
Yeah, now add more of this, so you have more of those guys.
All of that has become geometry.
That's right, I agree. But now add more of those.
So you can now consider like a deep brain on the LLM geometry. That's what they are.
No, but that's different because you're just considering big background, which has become the LLM geometry.
That's true. That's true.
And now you're considering an excitation on this. What else can it be but a string in this, a closed string in this background?
Yeah, you can have that, but that's a different question. They really like adding a single trace on top of the.
That's right.
Yeah.
But isn't that what he was doing? Because he was adding a very small excitation of that background. That looks like a single trace on that background.
I think what they are doing is like considering the open string that you would get when you add like an additional.
Well, I don't see that additional deep brain. Where is that additional deep brain operator?
So in the CFT side, each row in the Young diagram is a deep brain. And then what we're doing is we're attaching things to each separate row inside the CFT.
But if I remove that excitation, all I had was the LLM geometry.
That's true, but the LLM geometry has like different places where strings get
Sure.
stuck, right?
So that's different.
Those are the edges. Those are the edges.
So that's different places where the closed strings will be.
That's right.
Fine.
Well,
That's right.
Although if you take Navigato, so this should be
That's right.
describing a closed string, and you pick a string with arbitrary quantum numbers,
Yeah.
and you try to localize it at the edge, there is no solution.
Well, if I just take string motion in the LLM geometry, I take closed strings, they're still somewhere.
That's right.
There's nothing else you can do, right?
That's true.
But what they cannot do is, I don't think they can dynamically move from one place to the other.
I don't care.
Oh,
I
that's
just,
fine. If you don't care about that, that's fine.
I just want to know whether you're claiming that the motion of these closed strings in this background gives you the same spectrum as in AdS. That would be an incredible thing.
No, I would say that's not what we're claiming.
Okay.
I think the claim appears to me that there are certain solutions of that theory in this element background, we map the solutions in time space.
Yeah,
Right? Am I right about this, Robert?
So these really are open string excitations. So I mean, to give you an example, there's a difference between doing this. So you have the background, and you add some boxes over there, let's say 3 boxes. There's a difference between doing that and doing this with 3 boxes inside it.
okay.
This thing matches nicely with number go to action and its closed string motion on the LLM background. But this thing, I think we should really think about as having excited this row of boxes sitting out here.
Okay, that's what you
So see, there are closed strings that explore both places where strings get stuck, and those will not be there in ADS
So
5.
you've taken one D-brain out of the LLM background,
Exactly.
made it special, and put a string on top of that.
Exactly. And that thing agrees with N is equal to.
That's right. Thank you.
Any further questions?
So would you predict, so if you were to study this motion with this there are analytical integrability techniques, right? That, Basu Pandazaya started and all that. So you'd say if it's a just normal closed string, would you predict that it's integrable or non-integrable?
You mean just a normal closed string?
Yeah, a normal closed
I
string.
would say not integrable.
Okay, so but if we did, so to find some evidence of non-integrability, you say it's non-integrable?
Yeah, not integrable.
Oh, no, okay.
So this D-brain that you pulled out, is its geometry? I mean, something smooth. Is it nice, a sphere or something like that?
So we're pulling it out in the gauge theory in the CFT.
But then you do calculations of the on the bulk, right? Well, in that, what calculation should I be doing?
So these magnons, I mean, I guess it's similar to your story, Diego, where you could really think about these magnons as kind of being open strings attached to a D-brain.
But did you put in the shape of the D-brain? Is the shape put in somewhere?
So it's spherical and it's sitting at some radius.
Okay. And these open strings that go between from ends, do they go very? They don't go very far.
So if you take the open strings that stretch between different corners, they stretch between whatever corners you have in the space-time geometry.
Nice.
In that situation, the magnon scattering is inelastic. That, for example, is an example where you for sure don't have integrability.
Right. Thank you.
Okay, let's thank Jaco again.